started.
Right. I simply thought I will write down before we go over again. I didn't write it down many, but at least there are some. So AJ is a sequence as usual, a sequence of independent identically distributed m times m matrices. Oh, sorry. Right. Okay, so a sequence of IID matrices, m times m, determinant of AJ is 1, A of n is product of these matrices, we define this Markov chain, and we want to study the asymptotic behavior of this product. Once we apply it to x1 for a fixed x1, it turns out that under certain conditions, this is an exponentially growing thing. Norm of A of n is growing like e to the power gamma n. The conditions for this statement, I remind you, are that the group G mu is strongly reducible, which means that it doesn't preserve any finite union of subspaces of a fixed dimension. And non-compact. And I say again that G mu is a group generated by the support of mu, which is a subset in SLMR. In the group of these matrices, SLMR is simply a notation which means a group of matrices with determinant 1, real value, R for real. So we have this group, and if it is non-compact, strongly reducible, then for every fixed x with probability 1, we have this convergence. This is the first statement. And the second statement, gamma is strictly larger than 0. We have seen that if we introduce the following operator, Vj, by definition, Vjf of x is this operator. It is simply the integral. Oh, sorry. I went one step further than necessary. It is simply f of gx divided by the norm of gx times 1 over the norm of gx to the power m divided by p. Then this is a an operator which is LP of S unitary. It preserves the norm in LP. And I said that the spectral radius of another operator, V, which is the integral of Vj, V mu of j, you simply integrate this identity. If you want to know what is Vj of f, you simply put the integral here and you get Vj of f. So it's a simple notion. That the spectral radius, I don't think I used this. I will denote by R of V is the spectral radius of V. R of V is supremum of the absolute values of lambda such that lambda belongs to the spectrum of V. So what I was trying to explain, but will explain a little more than that, is that if no measure is preserved, if no measure is preserved by G mu, then R of V is less than 1. Then this operator has a spectral radius which is less than 1. Well, no measure on S, and I always mean probability measure. On the sphere. And we have discussed this, the meaning of this condition, G mu is strongly reducible. I explained exactly the proof of this in the case when m is equal to 2. But this really easily extends to the general case, arbitrary m. The meaning is simple. If you have stronger reducibility and no measure is preserved by G mu, then G mu is non-compact, then no measure is preserved by G mu. There is no measure that is preserved by G mu. So the main thing is to prove that the spectral radius of this operator is less than 1, and then we prove, then it will follow it then follows that norm of V to the power n behaves like, actually it behaves like R. It is a well-known fact that it behaves like R to the power n. One could say it is less than a constant depending on epsilon. If one wants to be very precise, I should write it like this. Strictly speaking, this is what is known. But if you are interested in log of this divided by n, it simply has the limit log of this thing divided by n, or you take a square root of n, root n from this quantity, it will simply converge to R. This is a well-known fact from the theory of, I don't know, elementary one. first steps of Banach algebras, but don't be frightened with that. This is a very elementary exercise, relatively elementary. Now, of course, from here, as I said, it follows that the probability that the norm of A of n x is larger than e to the power epsilon n will be smaller than e to the power minus delta n for some delta positive. This implies this inequality, and this means that for typical x, typical in the sense of Lebesgue measure, but this is sufficient for controlling the norm of A, and the rest is given by the oscillated theorem, the Kingman's subadditive ergodic theorem, and so on. But I will prove a slightly stronger result. I will ask the following question. Of course, we know. Once we know that the spectral radius is less than 1, we know that the norm will be decaying exponentially. The power of this operator will be decaying exponentially. But the question, and a very reasonable question, I will show why it is a very reasonable question, and I didn't invent it, is what is the k, the smallest possible one, such that the norm of v to the power k is less than 1. Of course, if we know this k, then obviously norm of v to the power n will grow, will decay exponentially. Once we know that such a k exists and what it is, can we find this k? We shall know what is happening with the power v to the v to the power n. Here we only know the existence. Of course, if it tends to 0 exponentially, at some point it becomes less than 1. In order to answer this question, I will introduce the following sequence of groups, actually. I will consider G1, which is a group generated by the following matrices: G1, G2 to the power minus 1, where G1, G2 belongs to the support of mu. So it is basically like the group there. But it is, in fact, very often much smaller than that. Because the group G, of course, contains this group. But I want first to multiply each matrix from the support by another matrix from the support, and only then generate a group. I can consider also G2, which is the same thing, but generated by G1, G2, G3 to the power minus 1, G4 to the power minus 1. Any matrices from the support, I will not repeat all of that, such that the same thing happens. All of them belong to the support. And I have another group, and it is obvious that G1 belongs to G2 because I can always take these two matrices equal to each other, and I will then get the matrices. I will simply get G1. And so on. I can consider GK, which is generated by these gk plus 1 to the power minus 1, g2k to the power minus 1. So that gj belongs to the support of v. So what I said, let me write it down. G1 belongs to G2, and so on. Belongs to GK, and all of them belong to G mu. And I don't even know whether this will be an infinite chain or not, most likely a finite one. But I don't care about that at the moment. Now, why do I need it? Because this is a way to state the theorem. Theorem suppose that gk does not preserve any probability measure on S. Then norm of v to the power k is less than 1. So the first group, which does not preserve this norm, gives you the k. If you know the group, it gives you the k for which the norm of v to the power k is less than 1. It is a very useful thing, though it is not very difficult. It is not, if you do it properly, then the proof is at least as simple as Wirtzer's proof of Furstenberg's theorem, actually slightly simpler. Just you have to do it in a different way. And Wirtzer has, as I told you already, simplified Furstenberg's proof. Let me consider an example. No, should have it. Ah, yeah. Still it is here. So if G1 is our beloved Q1 minus 1, 1, 4, let us say Gj, I will simply have some elements from Qj, I will denote them Gj, 0. Then, of course, G1, G2 to the power minus 1 will be equal to 1, 0, 1, 0. And here we shall have Q1 minus Q2. And we know already, that's what we have already discussed. So what will be the group G1? So G1 will be a group which contains all these matrices, and only them. Because matrices of this, just that it will be something of this form. 1, 1, alpha, 0. With alpha, which is, well, if you raise this to the power n plus or minus, you will have an n in front of this number. So alpha are some numbers there so that they form, they are such that they form a subgroup of the group of real numbers. Additive subgroup of the group of real numbers. Anything which is an additive subgroup of a group of real numbers can be there. Any arithmetic progression, rational numbers, whatever you invent will be there. Just it has to be an arithmetic subgroup. This is what can G1 be. We know that in this case, but it is never compact. And the only measure which is preserved by this matrix is it exists by all these matrices. It is a measure concentrated on this vector. Because this vector is a joint common, it's a vector which is a common eigenvector for all these matrices with eigenvalue 1. So there is no problem. So that means that I cannot apply my theorem. I cannot say that k is equal to 1. And it turns out that the norm of v to the power 1 is 1. Yes?
For this we need, let's say, at least 2 different GJs.
Yes, sure. No, I always consider a non-trivial support. So this is not a 0. Otherwise, it is not interesting. It's a, we don't want a constant potential. We know what happens in a constant potential without this theory. This theory is not needed for the case of a constant potential. Now what happens with G2? If you look at G2, it will be a group generated by these very matrices of this form, G1. Well, I have it here, actually. G2 to the power minus 1. In particular, the following matrix will be in, I will not write what G2 is, but let us look at it. Will it be helpful or not? The following matrix, G1, G is arbitrary, which is not, say, equal to G1. Actually, it can be, in fact, equal to G1. G2 to the power minus 1. I only, of course, do not want them to be equal to each other. I want to get something like that, in between. And then G to the power minus 1 then. So I took G1. In this sequence, I put G1 here, G2 here, G and G on the left and on the right. So it is a matrix of this form. Now, it is very easy to understand that just the powers of this matrix, they form a subgroup of the group. If I take all of that to the power n, this belongs to G2. And hence, there is a group which is equivalent to G1. This is a group which is equivalent to G1. It is simply, it is isomorphic to G1. And this matrix gives you an isomorphism. And at the same time, this is a subgroup of G2. Now, which measure is preserved by this group? The following unique measure is preserved by this subgroup. You have to apply G to this vector, sorry, 1, 0, and the measure concentrated with an atom 1 on this vector. And this is the only measure preserved by this subgroup. But G2 contains also G1. So there are two vectors which are possible candidates for having a measure which is preserved by the whole group. And both of them cannot be in the support simultaneously of this measure. And so there is no measure which can be preserved by the G2. No measure is preserved by G2. Hence, the norm of V squared is less than 1. Before I go to the proof of this fact, of what I said there, or at least try to explain the idea of the proof, I would like to try to understand what is the meaning of this thing for the random Schrödinger operator. Why do I want actually, why am I not quite satisfied with just the Furstenberg theorem? Because one of the meaningful potentials is the following one. You have minus yn plus qn, yn plus 1, yn, so qn minus e, sorry. This is our equation, yn minus yn to minus 1 equals 0. Suppose now that qn is a sequence of random variables which are drawn from 2. They are independent, but not necessarily identically distributed. Suppose you have simply a sequence of distributions attached to each point n, distribution functions, fn, and you draw your qn from these distributions. They are independent, but not identical, and not identically distributed. Well, the most interesting, or one of the very interesting examples is when there are just 2 of them, 2 different. Then the Furstenberg theorem doesn't work, because you need powers, it is designed so that it looks at the spectral radius of an operator. There will be no one operator. But it works, what I explained, works to the point when you have to look at the product of V, I'll put now V1, Vn, meaning that these guys are defined exactly as this operator V, but I will have there different j's. I can have, sorry, j. I can have them like this. Most of the theory will work. But the problem is, I will not know what to do with this product, with the norm of this operator, which now will be, instead of a power, I will have a product of these guys. But if I know that every 2, the product of every 2 is less than 1, then I have a very good chance to divide them into pairs. And in this particular case, if the distributions are not trivial, all of them, that means that these random variables are not concentrated on one singular point, they are really random, then all these guys, V1, V2, and then V3, V4, will have a norm which is less than 1. This will be less than 1, the norm of this, less than 1, and so on. And of course, it will, under very simple conditions, sometimes it will grow exponentially. Sometimes it will not. Because if they are all really different, you can have situations when there is no exponential growth, but there is also another interesting situation when Qn, say, is equal to psi n are IID, random variables, divided by n to some power. 1 over 2 minus epsilon is a very popular power there. It is a decaying potential, so the matrices essentially become orthogonal. Our matrices become, well, they are equivalent to orthogonal matrices. But what we do know is that still the product of each two has a norm which is less than 1. If we want the control, we can do it. It can be shown that in this particular case, the growth of A of n, and this is not quite a trivial statement, but it's true, is if these psi n are independent identically distributed, this will be e to the power of order e to the power n to the power epsilon. This will be the growth. Not a linear growth, but this one. And this all of that somehow fits into the framework of what I explained. I'm just, it is not very difficult, but effective or efficient estimates here may not always be easy. Now let me return to the theorem I have stated. I will explain the idea of the proof. What is it that I do not need here? No, I will still need this.
I need to ask a question.
Yes.
Why is it that this is not Furstenberg's theorem just applied with a translation which is twice as long as the original one, 2 years?
No. But they are not identical. This pair, the pair you have here, you have an operator, say, corresponding to matrix A1.
Yeah.
This corresponds to the matrix A2, the integral, right? But they are not identically distributed.
A1 and A2 are, right. But then the
And this pair is also, this is a third distribution. They are also not identically
well,
distributed.
I see, it's a third distribution.
Yeah.
Ah,
Third and fourth and so on. Because, well, for instance, this example.
yeah.
They are all different. They may all be different. It is also interesting when there are just two of them. Then you always have the exponential growth. If there are just two of them, arbitrary order, you have always the exponential growth. It is more tricky with completely general case, but there is also a result there, but I will not go into that. It's a much trickier, well, but it requires a set of new ideas, a trickier thing. But it is there.
Question over there. Sorry. Is this just for small epsilon?
Epsilon is positive.
Or if you put epsilon is a half?
Epsilon is positive.
Positive but small. So you can't
Yeah.
put epsilon as a half.
No. Sorry, I should have put.
No, minus.
No, minus, yes. No, I can have epsilon which is equal to the half, but then it is not interesting because this is the old case. It decays, but it doesn't decay very, very fast. This is the idea. You can have a decay here. I can write it like this. That is this psi n divided by an. And an are such that an squared is infinity. The sum of an squared is infinity. That is what is really important for this sort of result.
Psi multiplied by an.
Hmm?
Psi n multiplied by an.
Ah, sorry. Yes, thanks. Psi n multiplied by n. I could write it like this. Qn is equal to thanks. Right. Okay. Now I will return to the statement I made that if null measure is preserved by G k, then the norm of v to the power k will be less than 1. I will immediately say that k, for the proof, for the practical purposes, k is very important for applications. But for the proof for G1 or for Gk is the same. You will see from the proof for G1. So what I will prove is the following thing, which is not something that does not hold in the case of our example, because in this case, norm of v is 1. But the proof is the same for every k. It is relatively simple. I will not explain all the details of the proof, but I will definitely explain the idea. And it is relatively simple. Okay. Remember that Vj, if k equals 1, what I want to prove, so we want to prove that the norm of v, not the spectral radius, but the norm of v is less than 1. And this is the statement. I simply look at the theorem where k is 1. I remember, well, how do you prove it? Suppose that on the contrary, the norm of v is 1. What does it mean that the norm of v of an operator is 1? It is a simple definition. It means that there is a sequence fn of functions in LP of S. There exists fn in LP of S, n is 1, 2, and so on, such that the norm of each of these fn is 1, and the norm of v fn converges to 1. It is always less than or equal than 1, because we know that this operator has a norm. It preserves the norm of every function. Sorry, I was too fast. Well, what I said is it doesn't preserve the norm of every. It is always less than or equal to 1. Now, from here you can extract what I said if you know that suppose with E there. If you know that no measure is preserved by the group G1. If you know that, then it will follow that this is impossible. What is the idea behind that? You remember that I mentioned to you that Furstenberg observed the following non-trivial thing. Well, it's extremely elementary, but it is deep nevertheless. That he looked at this sequence of n, which in itself does not converge to anywhere. I mean, in a Hilbert space, it still converges. He looked actually at the Hilbert space, but it doesn't really matter. It converges weakly to somewhere. And he noticed the following thing. Let us consider the absolute value of fn of x. We have simply a function there. We can raise it to the power p. Then the integral of this function, d mu of x, this is simply the norm of f to the power p. And I said that I consider a sequence of functions with the norm 1, so this will be equal to 1. I will look at this over this theorem. It is a sequence of densities of a measure, of measures. Say kappa n with density Fn.
This d mu should be the surface measure, right? Not
Surface.
in your
Oh, yeah, I'm sorry. Yes. Thanks a lot. With densities Fn to the power p. And this, of course, has a convergent subsequence because S is a compact set, and you always have a convergent subsequence, so I can always think that this is simply converges in this sense, in the sense of measures. But I will, at this point, I will simplify my task to prove the theorem, and I will say, okay, suppose that not only does it converge to a measure, but suppose that this measure actually has a density. For simplicity only. It is an unlikely thing to happen, but if it happens, it simplifies the situation. This means the following thing, that in fact I have f such that the norm of v of f is not just less than 1, it is equal to 1. It's all what I want. What I will need is this thing. If I have this equality, I will see that the measure from here, I will deduce the fact that this measure with a density given by the absolute value of this function to the power p is preserved by the whole group. Now I can explain it easily. What is that? This is the integral, and I will put it in this form. It is Vj of f d mu of j. Integral over SL mn. What do I know about these guys? And I know that the norm of this thing is equal to 1. This is all what I want, in fact. What I know about these operators, they are such that they preserve the norm of f. The norm of Vjf is the same as the norm of f. It is 1. Now there is another not entirely trivial fact, but well and widely known. The uniform convexity of the LP space. It is a property which is easy to prove in a Hilbert space, in any Hilbert space. It is not quite as easy in LP space. And when I say LP, I already mean that there is another structure there. Because the Hilbert space is, of course, uniformly convex, but I will explain at least what is uniform convexity. Yes?
This f is the limit of the fn's, right? It's the weak limit of the fn's. Yes?
It is the weak limit of the fn's.
Right.
But all what I need from now on is that I don't want to look at measures because it is a slightly, just a little bit more advanced object. But I want to say that this this limit measure has a density. It is not essential for the proof. It is just for simplifying the explanation. But I can get this done for, and it's not difficult to get this done for the measures. So what I have here, okay, I don't need this example. What I now have here is the following thing. I have the integral of these vectors. Now I consider this as a vector in a Banach space, a unit vector in a Banach space. And this means that I have a measure on a unit sphere in a Banach space. Now, of course, if you have a convex combination of vectors lying on a curved sphere, the result will always be inside the sphere. When I say always, this is a tricky moment. Always if the space is uniformly convex. So what is uniform convexity? You have two vectors. Uniform convexity can be defined as follows. You have two vectors, f1 and f2. You take 1 over 2, f1 plus f2. This will be here. In a linear space, and it is enough to have it in a two-dimensional. I mean, the definition is absolutely two-dimensional. You don't have to think about the LP space. But then you want to say, what is the distance from this point to that one? And of course, it is very small. It will be depending on the distance between these two guys. So there are two distances here, delta and epsilon here. In a Hilbert space, this thing will be of order delta squared, if I'm not wrong. But uniform convexity means that epsilon is larger than f of delta, phi of delta, which is larger than 0. No matter what f1 and f2 are. And you can easily check that for a Hilbert space, this is always satisfied. This is a very, very important property of a sphere. You don't want to have a sphere like this. By the way, this is a sphere. But you don't want this. It is a sphere in a very good Banach space, two-dimensional Banach space with the norm of x1, x2 equal to absolute value of x1 plus absolute value of x2. And this is exactly what you do not want. You want a good, nice sphere there. And the sphere in a Hilbert space or in LP space is always very good and nice.
P greater than 1.
Sorry, with P greater than 1, this is exactly the case when P is actually, well, strictly between 1 and infinity. This is exactly the case when P is 1, by the way, of course. In my examples, LP is always from the very beginning. P is larger than 1. Okay, so in this case, what can you say if you know that the combination 1 over 2?
Another question here.
Yes?
I'll wait till the end of the proof and I'll ask this.
Well, I'm explaining a very simple thing. What can you say that if you know that your two vectors are in a well, uniformly convex space, 1 over 2, F1, F2, and suppose that you know that this is equal, they are units, that the norm is equal to 1. The only possibility for this to happen is when F1 is equal to F2, because otherwise it is strictly less. It is here. So this is exactly the proof, the idea behind this proof. If I have this equality, I have the following property, that all these vectors are the same. For any two matrices G, Vg of F is Vg1 of F is Vg2 of F. Vg1F is Vg2F for any G1, G2 in the support of mu. And what I said is essentially the proof. Yes?
Could you possibly repeat the last statement?
Oh, this one?
Yes.
Then F1 is equal to F2. Thanks, actually. It is useful to write it, not only to say it. So, you have this thing. What does that mean? I explained the proof of this fact now. Of course, I can be much more precise, but for a mathematician, it is enough. What I said is enough. It is a proof. For the purposes of learning all these things, you have to think of it. Otherwise, nothing will happen if you are interested. So let's put it like this. Now, if you have this, we can, of course, apply Vg to the power minus 1 to both sides and see what happens. I have now Vg2 to the power minus 1, Vg1f equals to F, sorry. I also know that Vg2 to the power minus 1 is Vg to the power minus 1. G2 to the power minus 1. This is easy. It has more or less every property of a representation, but if you are frightened with the word, don't worry about that. This is irrelevant. It is just this property that I need, and it is obvious. If you look at how I define Vg, you will see that if I want the inverse operator, I simply have to plug in g to the power minus 1, and I will have the inverse of this operator. And finally, I see that because this is Vg1 G2 to the power minus 1 F is equal to F. And what does that mean? That means that these two measures, that this function and this function, give the same measure on a space, and this means that you have to check it. And this is exactly the measure G2. Oh. Actually, it is the measure G1 to the power minus 1F. If I want to be very precise, I should say it is G2, G1 to the power minus 1 of the measure let's say mu f. Oh, mu f. Measure nu f is by definition the measure with the density f is equal to nu f. So this equality and this equality is the same thing. Which means that the product of these two matrices, any two matrices from the support, preserve the measure there, which is there is a measure, if, and all of that follows from the fact that I believe that there is, or that I suppose that there is a function such that this is equal to 1, a function f. Now, if there is no function f like that, and this is most often the case, you never have this function, but there is always a sequence of functions, and then this equality is nearly satisfied, and it is satisfied in the limit, but not for this thing which does not exist in general, but for the measure which always exists. This is how the rigorous mathematical proof goes, but the idea is there. The only thing is that in my proof, I wrote, in the statement, I wrote the group generated by the matrices, like this, right? Was it like that?
Yes.
Okay, then that's fine. I thought that I exchanged the places, but you see, it doesn't really matter. The idea is important. But it is also correct, I believe. So, the norm of this operator is less than 1 if there is no measure which is preserved by this operator. Now, as I said from the very beginning, for gk and for g1, the proof will be the same. What will be the difference there? The difference there will be that instead of g, I will have a product of k matrices. So what? I will have a product of k matrices there, but I can denote the product of k matrices by one letter. Say it will be g, and then repeat the whole thing. Okay, now we have a half an hour, and I would like to move to the strip model and to see what happens there when we do have not one exponent, but many of them. Already for these matrices, Hj, there are many exponents. And even for two by two matrices, but there are two exponents. One is positive and the other one is minus this one, minus the positive one. But the situation becomes more complicated when you consider the case of m by m matrices. So I will now explain how the matrices of order actually 2m by 2m arise in the localization problem on a strip. I will consider the following model. I will consider a strip with m lines. In my case, m is 3. But in general, there are m lines here. M, 1, 2, m. On my picture, it is 3. And there is a lattice there. And there is the classical tight binding model minus delta plus q on this lattice. And if you look carefully at each point along this, and you look not at one point, but at the points lying on this place. This will be number n. This will be n axis in this direction. And this I will call I. So every point, just a second, every point has two coordinates, and I. Yes?
What is the boundary condition for Laplacian in the...
0. 0. There is nothing there. 0 boundary condition.
could also imagine being on a cylinder, right?
Yeah. No. I will, at the end, it will be an absolutely arbitrary crossover. Arbitrary set with arbitrary interaction. I will try to state the theorem about the case when there is an arbitrary interaction, but there is a choke. A little more choke. You mean? I want the white one. No, there is a box here and a lot of choke, but this is not white.
Maybe around the.
Maybe, yeah, I'm sorry. No, there is a lot of it. Sorry, yeah. No, there is plenty. Yeah, very careful here with that. Yeah, no problem. Anyway, so if you look at what is happening here, if you write this equation, minus delta, plus q, you apply it to a vector y. Y will consist now of a sequence of vectors. I want these guys, the values, to be organized as vectors. So it is yn m, or yn1, yn m, n between minus infinity and infinity. Sorry, one has to define it properly, of course, so that everybody can read. If I look at this vector, yn will be itself a vector, it will be yn1, yn m. So yn1 is here, we have yn1 here, yn2 here. This is yn m. I number them from here to the up, but here they go in the opposite direction. That's just a tradition. And here, n is, let me use a short notation, n is in z. This is any integer. Now if you look at how this operator acts, and this operator is just the usual operator which you are supposed to be used to by now, the Anderson model, then you will see that this action can be written in the following way. It is exactly similar to what we saw many times in dimension 1. Because minus yn plus 1, the connection between these two vectors, plus qn yn minus yn minus 1, well, is equal to e yn. Or I can actually, in order to, I will write it like this, qn minus e. And then I'll put a 0 here.
Take derivatives only in the n direction? I mean, the Laplacian is a one-dimensional object in your...
No, just a second. I will explain. I simply rewrite. I don't do anything at the moment. I simply rewrite this equation, and I explain. This equation can be rewritten in this form, and I will explain what is Q. In the case of the tight binding model, just nearest neighbors interaction, this will be the following thing. Q, you will see, in the two-dimensional case, Q will be very simple. It will be just a Jacobi matrix, namely Qn if you look carefully, will be exactly this matrix. Q n 1, Q n m, minus 1, minus 1, minus 1, minus 1. The rest is 0. This is what Qn will be. So there is interaction across the line, and there is interaction in this direction. They are all bind together. And this is absolutely essential, of course, otherwise it is not very interesting. If these lines are separated from each other, it's not interesting. It is the same model that we already had in dimension pure 1. Oh. Now, of course, again, exactly as in the case of a one-dimensional model, of the one-dimensional model, I can rewrite this equation 1 implies the following relation: yn plus 1, yn. It is actually equivalent to this relation. Here I have Qn minus E, and when I say minus E, I mean minus E multiplied by the identity matrix. Minus 1, 1, 0, and you apply it to yn minus 1. And so, in order to study the properties of the solution, you start from somewhere, and you want to know what is happening when n is increasing. You have yn, or y0, y1, say. Here, you have somewhere there is a 0. You know these two vectors, y0, y1. This is 1, this is y1. This is a set of numbers. You have to study products of these matrices exactly as before. I will call them an, as I did before. This is by definition my an. And this is why it is important to study these products, because you want to know what is happening on a strip. Another simple model, but much more advanced, it turns out, than the pure one-dimensional model. You have products of matrices A of n, which are an, a1. Now, the very same thing will happen if I allow the interaction between any guys here. Here, I only have the interaction between, in this model, with this choice of the matrix Q, I have the interaction, which is described by these minus 1s, between the nearest neighbors only. But if I want to include a case of a three-dimensional cross, of a slab in a three-dimensional space, I should look at a more general thing. So the most general thing you can have in this model is simply when Q is a symmetric matrix. So I will not care much about, for a while, I will not care much about this particular case. I will say Q is a symmetric model. I want to state a theorem which I will then explain. But I first will state it. I'll explain the sufficient condition for having all the Lyapunov exponents distinct in this model. If the distribution, well, sorry, I should say what are the conditions. Let Qn be a sequence of IID m times n symmetric matrices. Suppose that support of Q is irreducible. And that the expectation of the log of the norm of Q plus 1 is final. I will be now relatively precise. Then gamma m is strictly larger than 0, where gamma m is the mth Lyapunov exponent in this sequence of matrices. I know that I haven't explained anything, I only stated something. If then there are many things here that I have to explain, I know. If, in addition, there are two matrices in support of Q such that two matrices, okay, I should denote them Q prime, Q, two primes, and the support of that such that Q prime minus Q2 prime is alpha times B, where B, I don't want to use the letter P for projector because it is used for many other purposes. So where B is a one-dimensional 1D projector, then all the Lyapunov exponents of A of n, of this sequence A of n, are distinct. Now, all what we have time now for is probably the explanation of the statements I made. There are many of them. First of all, I used the notion of irreducibility. It's a very natural thing and very simple thing. You say that well, no, first of all, there is a soup of Q's. Soup is simply
You mean the symplectic matrix, or the subgroup of the symplectic?
no. Q is my symmetric matrix. There. I'm talking about. I will be. I restrict myself to the model. I'm talking about these matrices.
Yeah, that's what I'm saying. These are symplectic matrices.
They are more general than that.
Surely, by the support of Q, you mean the support of the group
No,
of these.
no.
No?
I don't mean the support of the group. I mean the support of these simple things. Support.
Then you have to explain. Then I don't know what it means, irreducible.
Yes, I know.
But yes, I mean,
That's what I'm trying to explain.
there's two Q's perhaps in this theorem, or is there really only one? One is the probability measure, right?
No.
No? Okay.
This is the expectation with respect to probability measure. This is a norm of a matrix.
I see.
And
So
Q is exactly the matrix which is in A. A, if I don't put an index here, A is of this form, Q is symmetric, and Q belongs to the support of the measure which I have on the matrices Q. My measure is not on matrices A. It is. I can say that it is there. It is, of course, there. But essentially, if I want to know the measure, all what I have to look at from the very beginning, my matrices were of this form. Do I have them still?
yeah, you check everything.
No. They were of this form. A is equal to AN is equal to QN minus 1, 1, 0. And that means something very concrete. I don't want these matrices, these, all together to be reducible by one orthogonal transformation. It is a very simple notion, but a very natural one. You see, what I do not want to happen is the following thing, that there is a unitary matrix U such that U, Q, U is equal to, and then there is a block here. This is m by n, not 2m by 2m. A block here, and then there is 0 and 0 there. And this for every Q in the support of the measurement.
Yeah, so
Because
Q has no invariant subspaces. The set of
They-
Q
yes,
has no
this
invariant
set-
subspace in Rm.
Exactly. This is equivalent to saying that this set does not have, this set, the whole set. Of course, every of them, every matrix has a lot of invariant subspaces because these are perfect symmetric matrices. So all the vectors, all the eigenvectors are there. And any subset of eigenvectors generates a non-trivial invariant subspace there. But I don't want them to have common eigenvector or common subspaces, rather, not eigenvectors, common subspaces which are, well, all the same for all the Q's. They are fixed, and Q, you take Q from different places and you have it. What I am saying here is that if you have this property, it is a very natural property. Why is it natural? Because if I have it, I can simply make a change of variables. Yn is equal to Q Zn, or sorry, Q U to the power minus 1. Okay. What did I write there? I actually wrote.
Yeah, if you had this property, then you could decompose the system.
I
into two
could
parts, so
decompose this system into a smaller system. So I don't want this system to be decomposable. This is the condition. Otherwise, it is simply not interesting. So this is an absolutely natural condition. If it is there, I mean, if it is not satisfied, I don't care. I simply have a smaller system. Now, the other condition, like this one, is very often, most often satisfied. Because if I have matrices like this, right? Q1, Qm, minus 1, minus 1, minus 1, minus 1. And these guys are simply independent from each other. I can always pick them so that this will be Q prime, and in Q prime, and in Q2 primes, I will simply have a different number here, and everything's the same. Everything else the same. And the difference will be proportional to a projector. It will be then Q prime minus Q2 primes will be a matrix of this form. It will be alpha and the 1, and the rest is 0. It is a projector, a very simple one. If I have these two properties, I always have all the Lyapunov exponents which are different from each other, distinct, and the smallest one is strictly positive. If I only have the irreducibility, I cannot say that they all are distinct. They simply are not in general. And if I have the time, I will explain that. I don't believe that we will have the time for many examples, but there are simply examples of this. And this doesn't happen. But of course, the main thing I didn't explain is what are the Lyapunov exponents. To those who know that, everything is fine. To those who don't, I have to explain it. You see, I actually gave the general definition of the set of Lyapunov exponents. I will repeat it very, very briefly. And I will say what is happening in this particular situation. If you have a sequence of matrices A of n, and we fix an initial vector x here, I said it in my very first lecture, right? I take the norm of this, I take the log 1 over n. It is not very essential whether there is a limit or there is no limit. You can consider the lim sup as n tends to infinity of this thing. And this I call gamma of x. And I said to you already that in the case of arbitrary sequence of matrices, absolutely arbitrary, non-degenerate, you always suppose that they are such that this upper limit is always not equal to minus infinity or infinity. This will always be satisfied in our case. The number of values which this function may take is not larger than the dimension of the space. In our case, this means we have at most m, 2m different values. Gamma 1 is the maximum, and then gamma 2 is the next one. Gamma 2m in general. This is the general case. It may be that some of them will coincide or will be the same. Then I will have not this long sequence, but a shorter sequence of numbers. If you think of it, that means that most of the vectors will have this Lyapunov exponent. There will be a space. So there will be some vectors which will have this as a Lyapunov exponent and exactly one vector. Up to multiplication by a number. If I have all these inequalities, there will be one vector. Then there will be a plane such that every vector in this plane which is not proportional to this one, x2m, I will call it, gamma of x2m equals to gamma 2m. There will be a vector in a very specifically chosen plane where, well, it will be the vector in a plane which is generated by this vector and the vector corresponding to the previous Lyapunov exponent, gamma 2m minus 1. And every vector in this plane, except of the one proportional to this, will have the same Lyapunov exponent. Gamma of x 2m minus 1 will be gamma 2m minus 1 for every, and this will be the same where x is in the plane generated by xm, x2m, x2m minus 1. And so it goes up until we have a hyperplane for which any vector which is not in a hyperplane has this Lyapunov exponent. It is what I described here is called a flag. You have a subspace, another subspace which includes the previous one, next subspace, and it arises in a natural way in this theory. This is how it arises there. What I said there in the theorem is the following statement. First of all, I don't need the lim sup. It always exists, this limit. And it takes exactly 2m distinct values. But because we are in the symplectic case, I can also tell you that gamma 1 is minus gamma 2m. Gamma 2 is equal to minus gamma 2m minus 1. Gamma m is equal to minus gamma m plus 1. Now this is an additional statement which is a corollary of the algebraic properties of these matrices. I think I have to stop here and I will discuss a couple of things related with that thing tomorrow, and maybe we'll try to explain even that there are some ideas behind the proof of this. Whether I can really explain the ideas is a different matter. But at least to state that there are ideas is not very difficult.
No, it went away.
So
Yeah,
this
there
is
is
a
a
symplectic flag. They are symplectic subspaces. Every plane is a symplectic plane. So those of us who understand classical mechanics well are not. I mean, can immediately sort of do something with this statement. These the matrices A and I in the symplectic group, and so the eigenvalues. So first of all, the determinant is automatically 1. That everybody can see immediately. And the eigenvalues have this property. With every eigenvalue, you have the inverse also as an eigenvalue. You take the log, you get this pairing.
I want to explain this next
You will say
time.
all
I will explain that.
all of
I mean, I understand that for experts, all of what I said is either known or not necessary to explain. But since our lectures are not designed exactly for the experts, I will explain many of these things.
Would you regard the condition to have all the Lyapunov exponents different if you have sort of continuously distributed little qi? It should be a set of measure 0, which in this space of main.
What should be the space set of measure 0?
If you have continuously distributed sort of potential values at the sites,
Yes.
independently, then the probability to have two matrices whose difference is a projector is really very, very small, isn't it?
No.
What is that?
It is exactly 1.
I understood he
Of
just
course, 1
needs to
is
have-
not a very large
doesn't
number,
matter
but
how many there are, he needs just 1, that's enough.
what I said is that there are 2 matrices, exist 2 matrices in the support, such that the difference between them is a projector. So this, in your example, this condition is always satisfied. It is-
I guess the surprise is that probability does not enter here.
I didn't say
Probability
anything
plays no
about
role.
probability. I said only about the support.
Okay.
That's no problem. So, I confuse people with mixing probability with topology, but this is life. It mixes everything, even when you don't want it. Okay.
More questions, comments?
So are all the Lyapunov exponents relevant to the properties of the eigenfunctions, or do you just need to know is only one of them interesting for that?
In a sense, all of them are relevant. Because the one which plays the really essential role is this exponent gamma m. This is what is important. And because this is positive, strictly positive, strictly larger than 0, I didn't say that. That is why the green function decays exponentially, and that is why it is possible to have purely continuous, purely point spectrum there, pure point spectrum there, with exponentially decaying eigenfunctions. It is, yes?
Do the higher, the larger Lyapunov exponents mean you have states with faster decaying tails?
This is not, it is, strictly speaking, it is an open question. Do you have these eigenstates which decay faster than exponent to the power minus gamma m times n, whose decay is faster than that? We only have, at the moment, an inequality there. This is a very good open problem, in fact. If one wants to be honest, nobody has ever proved. I actually even made a claim one time, but never came to write down the proof. So you can consider it as an open question. Yes?
If gamma m would be 0, but the other Lyapunov exponents would be positive, would it be possible that due to gamma m being 0, you have absolutely continuous spectrum and embedded eigenvalues?
Yes, it is, but in this case, this will only happen if the system splits into parts. This will never happen in this system. We have the reducibility condition there, and there is a theorem by Catania and Simon that in principle, yes, it can happen. But it will happen only if the system splits. If you don't have the reducibility condition, it is not satisfied then. Then, of course, so if you, in other words, there is a very strong statement there. If you have a Lyapunov exponent which is 0, the system splits. It is reducible. Yes.
Can you say anything when m grows infinite?
Sorry?
Can you say anything when m grows infinite?
Oh, I would like to. This is a big open problem, as you may know. Yeah?
Probably the gamma m becomes smaller and smaller, and finite size scaling would predict how that happens. And this is how physicists try to, I mean, if m is the width of the strip, and you let the strip grow, somehow you're trying to approximate 2 dimensions from 1 or quasi-1 dimension. This is very interesting to us.
Yes.
Exactly this. But mathematically, it's not so easy, or maybe not even possible at this point, to prove much.
Yeah, but if you use the perturbation theory with respect to disorder, you'll find that the minimum exponent is proportional 1 over m.
You have a minimum, a lower
Yeah,
bound.
but
Uh,
so your perturbation theory should break it certain moment.
It's not only
one would.
proven by Chuck Newman.
I think that this will be.
Minimal. Doesn't matter. It's minimal Lyapunov exponent tends to 0 always. If,
This is
drive
Stas. Try to be more careful when you say always. You know that there is a strong disorder. It is simply not true.
No.
Right?
This is completely different story. It's not
Yes. Then let us
half gamma m.
talk about a completely different story in a different setting, because we are talking about this concrete model, and when this question was asked,
I said about the small disorder. As for strong disorder, just by Frederick Spencer, we conclude that minimum exponent is positive, yes?
No. Not
it's not exactly the same, but it is close to the same. It's not exactly the
I
same.
think that
So
the
it's-
key is waiting out there. And some of us may actually go to key. However, at 4 o'clock, we're having the next in our series of research seminars, and I believe that Christian Sader is today's speaker. And I think we hit it perfectly. It's like it's almost orchestrated. I think he will pretty
We
much.
have not very much to say after that.
Pardon? You don't have much to say. I think what he says is a natural way of continuing the story you've been hearing. So I'm very pleased that this is working out so nicely. And we can actually then have plenty of time to discuss, also among the experts. Only those who want to participate, of course, should come. But I hope that will be as many as possible. So I look forward to the talk at 4 o'clock.